Okay guys, I wanted to make another short video here on pH and pOH for our acid-base equilibrium chapter. In this section, we'll learn how to characterize the strength of an acid or base solution, and then we'll learn how to calculate hydronium and hydroxide concentrations, as well as the so-called pH and pOH of a solution. So this slide contains all of the definitions that we need to know. The main concept is that the strength of an acid is measured in terms of its hydronium concentration, and likewise the strength of a base is measured in terms of its hydroxide concentration. We learned about last time that neutral water, because it self-ionizes, the concentration of hydronium and the concentration of hydroxide are equal, and they equal 10 to the minus 7. And so we use neutral water as the baseline for a solution that is neither acidic nor basic. An acid will have a hydronium concentration that is greater than 10 to the minus 7 and a hydroxide concentration which is less than 10 to the minus 7. Contrast that with a base. For a basic solution, the hydroxide concentration is greater than 10 to the minus 7, but the hydronium concentration is less than 10 to the minus 7. So we associate acidic characteristics with a large hydronium concentration compared to a basic solution that has a large hydroxide concentration, at least relative to water. It's kind of inconvenient to work with numbers like 10 to the minus 7 and so on, and so we use a different scale to characterize acid strength and base strength, the so-called pH and pOH scales. This is a logarithmic scale. You take in the case of the pH, you take the hydronium concentration of the solution, you take the logarithm of that, which essentially brings down the exponent in the concentration, and you multiply by -1. For the pOH, it's defined similarly, except for you use the hydronium concentration in units of moles per liter. You take the logarithm, multiply by -1, and that gives you the pOH of the solution. So given these concentrations, you can calculate the pH and the pOH of a solution. You can also go the other way. Given the pH and the pOH, you can calculate the hydronium and hydroxide concentrations as well using the anti-logarithm. So you take the pH value that you're given, which is typically a number between 1 and 14, and then you take the negative of that number, and then you take the anti-logarithm, 10 to the minus the pOH. And you can do the same thing for the pOH to calculate the hydroxide concentration. You'll recall from the last lecture that the Kw expression for the auto-ionization of water is given here, and the Kw value is equal 10 to the minus 14, so the hydronium concentration is related to the hydroxide concentration through this expression, and so given one, you can calculate the other. If you take this equation and take the logarithm of both sides and multiply by -1, it gives you this result here. And so this equation is analogous to this one. It's just expressed on a logarithmic scale. And we see that the pH of a solution plus the pOH of that solution must equal 14. If we look at acid strength versus base strength on the pH scale, we have this result over here. We see that for a neutral water solution, the pH of the solution is 7 and the pOH is 7. That is, if you take the logarithm of 10 to the minus 7, it pulls down the -7, then you multiply by -1, it gives you a pH of 7, and the same thing for the pOH, since the two concentrations are equal to one another. For an acid solution, since the concentration of hydronium is elevated compared to that of neutral water, you wind up with a pH value that's less than 7, so we associate strong acid behavior with low pH. The pOH, on the other hand, would be greater than 7. For a basic solution, you get the opposite. For a basic solution, because there's a high hydroxide concentration, the pOH ends up being very small and the pH is large. So for a base would have a high pH and a low pOH. These qualitative relationships here and the quantitative ones up here are very important. Okay, so you need to really know all of this material quite well. You need to have these equations memorized for your assessments so that you can be given a hydronium concentration, calculate the pH, or vice versa, given the pH, calculate the hydronium. You have to be able to do the same thing for the hydroxide and the POH. And then you need to be able to relate pH to POH or hydronium to hydroxide through these two equations at the bottom. So this is a very important slide. On your assessment, there'll be, I don't know, something like 6 pH, POH problems that use different versions of these, that use these equations in different ways, and you need to be quite familiar with those. Luckily, they're short problems, though, as we'll see in a little bit. Before we get to the example problems, I just have a few graphics for you to look at and think about. This slide here is meant to illustrate acid strength in terms of hydronium concentration, hydroxide concentration, pH, and POH. So right here in the middle, we have pure water, which is considered acid-base neutral. The pH is 7, the POH is 7, and the hydronium and hydroxide concentrations are both 10 to the minus 7. As you go up in this scale, so we are increasing the concentration of hydronium, we see that we go from things like rainwater to orange juice to stomach acid to vinegar to 1 molar HCl. As the strength of the acid goes up, the concentration of the hydronium goes up, and we also see that the concentration of the hydroxide goes down. And that's because of the Kw relationship. On the pH scale, the trends are reversed. For a strong acid, the pH has a very low value. So 1 molar HCl, which is very acidic, has a pH of 0. The POH, on the other hand, increases as you become more acidic. Okay, so if the pH of a solution is 0, then the POH would have to be 14, based on that relationship that we looked at earlier. Conversely, if you're talking about basic solutions, so as you go down in this table, the solutions become more strongly basic. Here, the 1 molar sodium hydroxide is a very strong base. We have the opposite trends. You have a very high hydroxide concentration relative to pure water, and a very low hydronium concentration relative to pure water. Also, the pH takes on a very large value, 14, and the POH is very low. So small POH means a strong base, just like small pH means a strong acid. And so you want to keep these trends in mind. This slide here is just meant to illustrate that there are different approaches to measuring the pH of a solution. You can have things like litmus paper here, where you dip a specially treated piece of paper into your solution and it changes colors, and based on the color change you can identify the pH to within about 1 sig fig. There's all sorts of acid-base indicators which will change to different colors when you put them in an acid or a basic solution. There's also digital pH meters here. This one is relatively cheap, and it gives you about two decimal places of precision. This more expensive one gives you about 3 digits of precision or 3 decimals of precision in your pH values. So you can measure pH using different tools. Well, here begins our example problems, and so this is a typical short numerical problem that you can expect to find on your assessment. So here we're talking about stomach acid, and they want us to calculate the pH of stomach acid, which is mostly hydrochloric acid, given that the hydronium concentration is 1.2 times 10 to the minus 3. So you need to have the definition of pH memorized, and then you simply substitute in the concentration into the hydronium slot here, and then take the logarithm using your calculator and the minus sign, and your calculator is going to spit out a whole bunch of decimals. And so what I wanted to add to this was how to choose which of these digits are significant. And the rule is you have to count up the number of sig figs in the concentration. So this particular concentration has 2 significant figures. That should equal the number of decimal places in the pH. Okay, so since I have 2 significant figures here in this number, I should have 2 significant decimal places in the pH. Let's see, in this problem, we are going to be doing the opposite. We are being asked to calculate the hydronium ion concentration of blood when the pH of the blood is 7.3. So this is a slightly basic solution. The term alkaline is a synonym for being basic. So we've got a pH of 7.3, slightly greater than water, and they want us to calculate the hydronium ion concentration. So we take our pH definition and we need to algebraically rearrange it to solve for the hydronium concentration. And this is the result here. And what we do is we take the pH and we substitute in the value. So you type in minus 7.3 into your calculator, and then you use your anti-logarithm button to calculate this result here. It gives you a bunch of significant figures, and this last part here is choosing which of these digits are significant. And so remember, the rule is the number of sig figs in the concentration must equal the number of decimal places in the pH value. So since we have 1 decimal place that's significant in the pH, we should have only 1 significant figure in the concentration. And so that's why I rounded it down to 5 times 10 to the minus 8 moles per liter. In this problem, we're working with POH and pH. And so this example wants us to calculate the POH and the pH for a potassium hydroxide solution where the concentration of potassium hydroxide is 0.0125 molar. Okay, so I went ahead and have shown you the dissolution reaction for potassium hydroxide. For every mole of potassium hydroxide that dissolves, you were going to get 1 mole of hydroxide. And since potassium hydroxide is a very strong base, if the concentration of potassium hydroxide is 0.0125 moles per liter, then the concentration of hydroxide will also be 0.0125 moles per liter. Given the hydroxide concentration, we can calculate the POH by taking minus the logarithm. That calculation is shown here. Our concentration has 3 significant figures in it, so our POH will have 3 decimal places that are significant. To calculate the pH of the solution, we use the relationship between pH and POH, where the sum of pH plus POH must equal 14. Here I've algebraically rearranged it and solved for the pH. So the pH is equal to 14 minus the POH. We just substitute that in and we get 12.097. And so just as we discussed previously, a strong base solution has a low POH and a high pH. Here's another example, and this one often trips students up. Okay, so this one, commonly, there's some common mistakes in this problem, and so I've only worked through the mistake portion of it. So for barium hydroxide, we're just going to repeat the calculation using the same concentration, but for a different base. So barium hydroxide, you'll see here, for every mole of barium hydroxide that dissolves, you get 2 moles of hydroxide. So there's a 1-to-2 stoichiometric relationship here. Previously, there was just a 1-to-1. And when there's a 1-to-1 relationship, you can just say that the hydroxide concentration equals the concentration of the potassium hydroxide. In this case, there's a 1-to-2 ratio. And so the hydroxide concentration will be twice that of the concentration of the base. And so we need to take that into account before we calculate the POH. So the common mistake is to forget about this factor of 2 that you need for the barium hydroxide. After that, the problem is identical to the previous one, and so I'll just leave that as an exercise for you to work out. Okay, so we'll stop this one here.